Hey, the recordings are recording. Excellent. Okay, so what we're gonna do is a grand canonical ensemble. We gave this another name. This is also called the Gibbs distribution. And what we're going to do, we're now going to let particle number vary. And so what we're going to do is that here's going to be a reservoir. Here's a reservoir, and you have all these particles here. So there are going to be NR particles, and the reservoir is at energy E sub R. And then what are we going to do? We get to be a mime. So we get to go like, system. So we just basically make imaginary walls like this. Actually, this. Put it on a different color. I can say here are some imaginary walls, and we call this the system. And what we're going to say is that the system has some number of particles n sub s and some energy E sub s. And what we're going to do is say that the particles can go all around. So when we do this grand canonical ensemble, the particle number and the energy, they'll fluctuate. Because energy can go in and out, and particle number can go in and out as well. That's what it's going to allow us to do. And so what we're going to say is that the total number of particles is nr plus ns. The total energy, and again, for the entire system, I mean, is going to be er plus es. And n and capital N and capital E will both be constants. Okay, so we started something last time. Last time we had our Gibbs distribution. We don't have that at all. We had our Gibbs free energy, and that's a Legendre transformation. And how do we define it?
That's H minus T.
This is our H minus Ts. Okay. And if you remember what we did, we showed that if you look at the partial of G with respect to N, that is equal to
mu.
This is equal to mu. And mu is by definition the chemical potential.
So that's the coefficient in front of a differential in the definition of internal energy.
Correct. When we trace it all the way through. So remember where did this come from? That recall, okay. When we had our first law, we had our TDS minus PdV. But how else did we say we could change the internal energy?
Add or remove particles.
We could add particles or remove particles, and we said that's going to be connected with this quantity called mu. So we did this, we traced it all the way back into here. Everyone happy with that? And when we did that, okay, what was our DG? I don't remember what it was like. It was VDP
Minus SDT.
minus SDT plus mu dn. Okay. So, and everyone's happy with tracing something like this through. What do you think your chances of seeing something like this on the exam on Thursday? Very good. Probably on the lower side. Okay. You might want to know how all these things get traced through. Okay. I don't understand it, but I'm confident one of you will. Because somebody has to get this right so I can get an answer key on this thing. I've had key in many of my classes. It turns out key does a pretty good job with all the classes I teach. Okay. It's like Dr. Staff. Dr. Staff is a master of many things too. Okay. So this is the function of P, T, and N. And then how did we get this equation here? We did the exact differential. And what do you think your chances of doing an exact differential are? Probably up there. Okay, so this is our partial of G with respect to PdP. Partial of G with respect to TdT. And then plus the partial of G with respect to N. Yeah. Okay. And when we did this, what's being held constant here?
Pressure and temperature.
Pressure and temperature here. Now, why was that important?
That's of the system, right? So we're talking about the system.
Yep. Okay. Now, we said normally with G. Okay, G is what kind of quantity? An extensive quantity or an intensive quantity, and what's the definition of E?
Extensive, it changes, varies with particle number.
Yeah, this is going to be the size of the system. And if you have something extensive, it's going to scale with the number of particles. Okay? So this is going to scale the number of particles. Okay. Now, what does it mean to be intense? So this is extensive. It's basically depends on the size of the system. Extensive. Okay. Then what did we say is intensive?
Doesn't do that.
It doesn't do that. What's like a classic example of this? Temperature,
Pressure.
number density, pressure, things like this. Okay. So intensive. Do not scale with the size of the system. So we said number density, pressure, temperature, things like that. Now, why did we make use of this then? Because I could say, and this is the important piece here, I could say that this G here is going to be some N times some function of P and T. Now, why couldn't I do this with the other cases? Why can't I do this with energy? Why can't I say that energy is going to go as N times some function of the entropy and the volume and so on and so forth? So we can't say this. Right? We come over here and we say, oh, well, and the energy depends on entropy and the volume here. So why can't I say that the energy then is N times some function of S and V? Why is that entirely wrong?
Because
SMV depends on N.
Yeah, the entropy here is extensive, so that depends on N. The volume also depends on the size of the system as well, or in many cases. So there's no way I can do this. I can do that here because basically of what I have up here. Okay, that I have two intensive variables here. That's a really, really subtle point. Okay. Everyone happy with that? So what did we do? We put this into here. So this gave us this partial of G with respect to N. This is our partial of N times F, back to N here. This is our mu, and this gives us that our F then is mu. And so what we can conclude is that this G equals mu times N. Okay, and that's where we left things off on Friday, almost. Okay. Questions? People look broken on Friday, so
That's okay.
it could have just been because it was just Friday, but. Now, then what did we do with this? We can take this G and put that into here, and we're going to get one relation. What we can do here, since I have this, we just said that this G is mu N. What is my friend H?
U plus PV.
U plus PV minus TS. And then what did we do last time? We kept,
U constant.
yeah, we're going to keep P and T constant. And why do we do that? Because we know that the DG is going to be 0 in that case here. And then the volume of the system is also constant, so as V as well. Okay, we're going to say we're going to have a finite size. And what I'm going to do then is I'm going to then keep U constant.
Wouldn't holding these three PT and V keep U constant? And like it depends on volume and entropy. So does that ensure constant?
I mean, it
entropy?
would depend on, it might be depending on the equation of state that you would have.
Okay.
But I mean, like for an ideal gas, probably would. So that's totally over constrained. In a case like this, I don't think in general, not necessarily. So if we do that, what did we do? I can then take the partial of this with respect to N. So take the partial of this with respect to N, keeping U constant. And what did that give us? That gives us on this side what?
Mu d.
Mu equals this term is
Yeah.
0. This term is 0. This term is minus t partial of s
With
with
respect
respect
to
to n. This is that constant. Okay.
I think it's my answer.
So what I have here is that then the partial of s with respect to n at constant mu equals minus mu over t. And we're going to need that today.
Constant mu, p, and t.
Okay. So is everyone happy with that?
We did on Friday.
Yeah. I like to live on the edge, Dominic. I don't think I should have to do just one way. I think I just like to just be out there. Okay. Yeah.
What's that from?
Okay. That makes sense. So this is where we left things off on. We got this expression here. Okay. This expression isn't used a whole lot, or isn't known as much. Okay. So what I want to do is use this, and then also our thermal, our temperature relationship, and I want to show you where the Gibbs distribution comes from. Okay. Now we can start the actual new class here. Okay.
And that's still all in equilibrium.
This is, we were only doing equilibrium here. So when we go to glass, it's going to fall apart. So we're going to have to figure out how to fix it up. And often the way we're going to fix it up is to introduce this awful thing called effective temperature, which I just despise.
Okay.
But people do it, so you have to do it. Okay, so let's proceed. So you will show in a future homework / daily homework, I don't know which, I'm in the process of running it up, okay? That if you have two systems and thermal and diffusive equilibrium. Well, you shouldn't say diffusive equilibrium because we're going to get this. But in thermal equilibrium at constant P and T, then mu1 is going to equal mu2. Let's say I have two systems like this. Here's a membrane. This is 1, this is 2. I'm going to be at thermal equilibrium, and then what's going to happen is that when this whole system is at equilibrium too, what's going to happen is that the mu1 on this side and the mu2 on this side, these are going to equal each other, and this is going to be called diffusive equilibrium. It's not actually that hard to show, but it takes a little longer than I want to do. So and I want to get to energy landscapes tomorrow. Okay, so you're going to prove the statement here. And you probably most of you already know this statement already. Because you've had thermodynamics, you've had either chemistry or some other stuff, so you most likely have that. And I'm going to have you draw it anyways. Okay, so that said, let's go through and apply this. Let's go back and draw our little picture. So here's our R. And here's our S. We're going to assume R and S are in thermal and diffusive equilibrium. And you're a constant P and T as well. So what does thermal equilibrium mean again?
Temperatures are the same.
That T of R equals T of S equals T. And then what about the diffusive equilibrium now that you're going to prove?
Number of particles.
Well, mu R equals mu S equals mu. And I want to ask you a question. What question do you think I'm going to ask about S?
What's the probability of?
What's the
finding-
probability?
of Finding S in a particular quantum?
Yeah, but I want this to be in a particular quantum state I. So let's ask, what is the probability? That S is in a particular quantum state I, which has an energy, I'll say E sub I. This is really my E sub S value. And particle number. N sub I. Now I say a quantum state, there's kind of two things just to specify. The energy and then the particles in that state. Okay. Hey, I think you're pros at how to do this here. What is that going to be proportional to?
It's generosity of that system.
Exactly.
Of
So
the
this
whole-
probability has to be proportional to G of R at some NR here and ER. Okay. And then some S and some NI and EI. Okay. This is exactly the same as
The canonical.
the canonical distribution. What's another name for canonical? Boltzmann. Okay. Would that maybe be a nice thing to know the derivation for on your exam on Thursday?
Yeah.
Yeah, I think you might like that. Okay. Now, we've seen this argument before.
That's fine.
How many ways can that system S be in one particular quantum state I? One. Right? And that's the key to this. So our probability here to be in this state I is directly proportional to this G of R, NR, PR. And what do we know about this reservoir compared to our system?
Big.
It's really, really big. When we do this thing here, this R is larger. It's much larger. Like this. And what will that allow us to do? Basically treat R as
Canonical.
the microcanonical ensemble. Right, so let's say our little system here is this atom right here, not this one over here,
Okay.
this atom here.
Right.
Okay, pretty much if energy goes in and out of that atom here, and this is the reservoir, that reservoir is not going to really change any.
Mhm.
Okay, so it's very safe to just treat that whole rest of the room as a microcanonical ensemble. Hey, but we're pros at this now. You tell me the implication of this. I know that the partial of S with respect to E is
1/T.
1 over TR, which is 1 over T. This is for
Microcanonical.
and thermal equilibrium. So this is thermal equilibrium. Yeah, but I know this system's also in diffusive equilibrium because you're going to show that in daily homework or homework, one of the two.
Partial G with respect to I.
You know that the partial of this with respect to
And oh.
an R is minus this mu R over TR, which is minus mu over T.
So very specific conditions.
Yes. Now, what can I say about SR and these equations? That this is basically microcanonical. SR is
Oh, ln of or KBT ln.
KD ln of
G.
GR.
Okay, cool.
I can put these in here. That one, and I have this one here. Okay, I'm gonna take the KB over on both sides here, and then what do I do with both of these?
What's the subscript on the E?
What's the subscript on the E? Oh, that's a little incomprehensible. Yeah, you wanna, it's this.
Okay.
Don't confuse it with this guy though. Okay, a lot of people think it's this, and then you're just being a jackass at that point. No, no. When you see me write something incoherent, call me out, please. Okay. That's utterly incoherent. I would actually argue I wrote a P there. Okay, but look what I can do with my magic marker. Crazy. So I'm going to take this one here. I'm going to take up the KB and then the partial of respect to either. So this is going to be my partial ln of gr equals our partial er of the kbt. And then my buddy here becomes the same thing, but with it. Now, this will be a good review of Calc 3. Okay. What do I do now with this? I integrate it. Okay. Well, what am I integrating this with respect to? ER. So this would be the ln of gr plus ER over KBT. Now, what can I always do with an integral? I can check it by taking a derivative. If I take the derivative of this with respect to ER, okay, there could be another term here. What could that be?
Any constant.
A constant, and also,
Oh, something is not a function of ER.
correct, in other words, maybe a function of NR. So there could actually be some function here, I'll call it F of NR, plus some constant C. Does that make sense? So if I differentiate this with respect to ER, keeping NR constant, this will give me 0, this will give me 0, this then goes to here. Does that make sense? Okay, now you tell me what's going to happen over here. If I integrate this will give me the ln of gr equals, and you finish that one.
Minus mu NR over KBT.
Minus mu nr over kbt.
Post function of ER.
And so some function, I'll call this h, a function of er, plus some new constant d. That makes sense? Because if I differentiate this with respect to nr, this is 0, this will give me 0, and this goes to that.
Differential equations.
Remember that from Calc 3?
Differential equations mostly. Calc 3 is more geometry space.
Okay. Good. Then if I compare these two together, this f of nr has to be this guy. And then this has to be this up here. And then my constants have to be the same as well. So what I have here is that the ln of gr equals er of kbt minus mu nr over kbt plus some constant I'm just going to call c. Does that make sense? Now I'm going to write this in a slightly more user-friendly form. I'm going to write this as beta er minus mu nr. What would be a good way to write a constant?
Sorry.
In terms of another constant, what other way might I want to write this constant?
Yeah, see.
The ln of a new constant, I'll say b, and I'm going to put a random minus sign in there. We're going to call it a plus sign. Okay. And now, why am I writing c as the ln of another constant b?
But we're gonna take, yeah, we're exponentiating. So
Yeah, so when I take this over to the other side, what do? I get the ln of gr minus the ln of b, which is
GR
GR over.
the log of the ratio here. If I do this, this gives me the ln of gr over b. Finish it up. What do we do?
Exponential.
Exponentiate both sides. Boom. There we be. Does everyone see the logic? Okay, it's quite beautiful. Now, do we know anything about ER? It turns out we don't. Look, class is over. Look at this.
E minus.
Yeah, this ER has to be the energy of my whole system E minus the energy of my system ES, which I'm calling EI. And what about the NR term? Yeah, my NR is N minus NI. Okay, so I can put this all into here. This gives me E minus EI minus mu N minus NI. Hey, and what could I rewrite this as?
Another constant up front and just get rid of the constants in there.
Yeah, this energy is a constant and this N's a constant, so I'm gonna pull all those things up front. So this is gonna be B, e to the beta E. And then this one is gonna be a minus and another minus, so the e to the minus beta N. Then I get an e to the beta minus EI, minus making a plus mu NI.
I think you need a beta in front of that UN.
Yes.
Yep. But since I have marker, watch what I can do.
That's spectacular.
That makes sense? Now, what do I know about all these terms in front?
This is you constant.
Constant.
Okay. The constant. Okay. These are all constants. And I'm going to pull out a minus sign out of that exponential term. That's what I really have. That this GR is some constant term I could care less about. Okay. E to the minus beta, EI minus mu, and
We'll also do this with the round multipliers.
yes, we do. Good.
Okay.
Okay. We won't do that because it just, we don't need that for this.
Yeah.
So now we can go back to this fellow here. So now I consider that my probability to be in the state, which is proportional to GR. This probability here is really going to be some proportional, this is just a constant, to this e to the minus beta, EI minus mu. Now you tell me how to finish this proof.
Need them to add to 1.
Correct. So we're going to have some sort of normalization constant. I'm just going to call this capital. Well, I call it N.
Capital M.
Capital M. We'll call it capital M. For normalization. The normalization. So if we normalize it, okay, if we normalize it to this. Okay,
I don't know.
so this is normalized. Normalization. It's always important to use correct words for these things. A lot of people don't. Messes some things up. Okay, how do we find the normalization constant? And this is going to be for some state I.
This has to be summed over all the states.
We have to sum over all the states. And what is this going to be? It's going to be kind of well, I'll show you what it's going to be. It's written kind of funny out and things. So we know that if we sum up all these PIs, we have to get 1. That. So what this tells me is that this normalization constant is 1 over the square root of I, e to the minus beta, EI minus mu NI.
No square roots at all.
Okay.
You just said
That's
a
where
square.
I did?
Yeah.
Really?
Someone.
So I told you before, I think there's an oral version of, I think, dyslexia. Which I think I have that in spades, actually. Okay, now what does this fellow here look like?
Like.
It looks like a partition function. Hey, but this is the grand canonical partition function. So what might that be a good name to call? The grand canonical partition function here, because this is our ensemble. So this is our grand canonical partition function. And you'll see two symbols for this. You'll see either a script Z.
Put more Russian letters in it.
That's Russian.
Also, as well as English.
And I probably won't do that because I can't easily get that font. Or favorite one, capital C. This is a lowercase. Don't use the lowercase. The lowercase is this. Okay. It's like a KS in Greek.
Yeah, you're a Greek person.
So. So this is going to be this guy here. This is one of the few times you get to use this letter. The only other case you use this letter is in particle physics. There's actually a particle like this that people study.
Well,
For the
just
most
like
part. 3 lines.
that. Okay.
It's made of 3 quarks. So this is what we have. Now, often if you look in books, this I here, so this I is often replaced with ASN. Okay. And what do you think this stands for? All basically states and n number. So basically you're summing over all possible values of the energy and the particle number. So I'll either write it like this, or I'll write it like this. You'll see this frequently in a book. Okay. What we're left with is that our probability then is this fellow here. These are basically this is your grand canonical distribution. Or it should say ensemble. Well, I'll say distribution. Okay, or the Gibbs distribution. Now, one thing we're going to be, any questions to that? Now, one thing we're going to be interested in is actually looking at the average number of particles in a state. So let's ask what is this? And you're going to tell me exactly how to calculate this because you are pros at this. And I'm going to show you a neat thing.
Sum over all possible states.
Yeah, any expectation, any thermal expectation value or thermal average. It's going to be the sum of all the possible energy values and then all this jazz times
Probability of that state.
and I. P I. That's our standard result. Okay. What we're going to find when we go to glass is that we're still going to have the exact same equation. The problem will be is that these are not going to be given by the Gibbs distribution or the Boltzmann. It's going to be given by something else. Although we're going to cheat sometimes and put in the Boltzmann distribution, but we're going to mess up the temperature with the fictive temperature. And then I just, well, oh well, we'll worry about that later on. But I'll show you how to calculate these P's in general. That's what took John and I forever to do. But there is a way of actually coming up with what they are for a system. Ain't easy. We got unlucky by the system like back thought. I'll show you how to do it. Okay. Now, I think you see something here. It'd be really nice if all I had to do is worry about calculating that partition function, if I could manipulate it somehow. Let's look at this.
Maybe
Let's ask what is.
put it inside of natural log. Is that a crazy idea? Take partial derivatives.
Who wouldn't want to take the log of the grand partition function and then take the derivative with respect to mu? Pretty obvious thing to look at. I'm kidding.
I wouldn't want that.
I'm even put a question mark after this.
Questions and with question mark. That's great.
One of my friends in grad school like playing the question game where you only answer in terms of a question.
Alright.
And he was ridiculously good at it, and it drove me nuts because it just won't stop.
Really?
Yes. Well, okay, so let's do this. This is partial with respect to mu. The sum on, not that at all. The log of the sum on I, e to the minus beta, ei minus mu, and I. Okay. You tell me how to take the derivative of that. Okay,
So
just a regular logarithm. How do you take the derivative of any logarithm? The argument
goes on.
goes in the bottom. Okay, what goes in the top? The derivative of this whole thing here, with respect to then mu. That sum on I is going to come out here. And what goes in front?
1 over beta.
You get a beta here,
And
and then I. I'm taking a mu derivative.
Right.
Times
E. Oh, you're taking it out.
e to the e minus beta ei minus mu n I. Okay, the beta is a constant, so I can pull that out. This is a sum on I. And I. Here I have this exponential part here. Does this have a name? That's a grand partition function, so I can take that inside the sum because this doesn't fit on I anymore. I can do this. Does this have a name?
Yeah.
Probability.
That's my probability. So this is beta. Sum on I. NIPI. That's what this is here. And what is beta? 1 over KBT, so I can take that to the other side here. This tells me that, right? So this is really beta expectation value of n. This tells me that the expectation value of n is KBT partial with respect to L1 to C, respect to mu. Okay, we're gonna get a lot of mileage out of that guy. Questions?
Mercy?
What?
Mercy?
No. Why would you even ask for that?
Questions about what I did there? Now we're gonna drive to, from this, we're gonna get two very profound things in this. Let's see, let's see, you might know it. I'm not asking about your background and you. Okay. You were not there. And you were there. You people should know.
What would be in there?
We're gonna do two cases here. We're gonna drive the Fermi-Dirac distribution
Oh, yeah.
with almost no work. And then the Bose-Einstein distribution with almost no work. Okay, so I want to show you where they come from. Okay? And then we're going to help out Etchem. Okay, Because she needs to calculate heat capacities for systems.
Yeah,
And let's see how we can actually use this to help Etchem calculate the heat capacity for her
Wow.
system. I wasn't gonna do this with enough help, we can help you out. So let's do two classic examples here. Okay, one is gonna be the Fermi Dirac distribution. We're gonna show you where that comes from, and it's just this equation here. And it's ridiculously easy how we're gonna get it. And then the next one is not a whole lot harder, it's gonna be the Bose-Einstein distribution. Okay. So we have to get two different things here, two different words that we've already mentioned before. Okay, how did we say we can view a particle in physics?
as a spinning ball.
A spinning little ball. Okay, so here's our little particle that's spinning. And this is the angular momentum of the ball. Okay, what do we call the angular momentum of the ball? We call that S the spin. We call this the S vector here, so S, that's all this is here, your S is your spin. Now, you can show, and we ain't gonna do it, because that's well beyond the scope of this course, that the magnitude of this S, okay, is equal to what?
S.
Well,
Script
H
F,
bar,
H bar.
which is what?
H over 2 pi.
Planck's constant over 2 pi times
Square root of
square root of
script S times S plus 1.
script S times S plus 1. And that script S is called the,
Spin angular moment.
well, the spin quantum.
Spin quantum moment.
So it's S here. It was a spin quantum. I'm just gonna state this as a fact. It turns out, can you have any S? Can I have like a third? No. Okay,
Only
you cannot.
you can
Okay, the
integer-
only thing you can have for S are
half integer and
half integers and full integer. For a while in the 90s, people were talking about anionic systems, where the S could actually be anything, hence an anion. I think that theory, fortunately for everyone, went away, and everyone drew the sigh of relief. Okay, so there are in nature three types of S.
Thing to do it, you can get it, scientists figured out how to get it, with like a third and a quarter.
yeah, they're so they just
Like it's a
released
very
new-
recent discovery.
I heard that paper was rejected.
Uh-huh.
We got a vintage
Yeah.
here.
Being projected by Wonderland.
So in other words, S could be 0, 1, 2, like this. We call these particles bosons. We could also have half integer S. So S could be a half, 3 halves, 5 halves. Okay. Can it be 6 halves?
Yes.
That'd be 3, and then that'd be a boson. The half integer particles are called fermions. Okay, what do fermions do that bosons do not?
Obey the Pauli exclusion
Yeah,
principle.
fermions, in other words, you have to have identical fermions, meaning all electrons, all protons, all neutrons, all the same particle. These right here, these obey the Pauli exclusion principle. Okay. But sometimes I think people get finished with chemistry and they think that only electrons obey the Pauli exclusion principle. No, it turns out any fermion will obey the Pauli exclusion principle. And what does it state? This states that no two identical fermions can have the same set of quantum numbers. Now, for those of you who are a little more quantum mechanical savvy, what does it really state?
That
I grab this one here and switch them.
the wave function takes up a minus sign.
Wave
So
function gets a minus sign.
the average state of both possibles is 0.
That's not part of it, but it's really the exchange gives you the minus sign.
Yeah.
Okay,
But if it does pick up a minus sign, then you take an average of those two states, that's a 0.
depends on what you're taking the average of. Okay. The bosons, what do they not do? They don't obey the Pauli exclusion principle, meaning if I have one state, I can put as many bosons with the same quantum numbers in there as I want. What's that one the basis for?
Bose-Einstein condensate.
Bose-Einstein condensate. This is also part of how the closest thing you can get to that in nature is liquid helium-4. So liquid helium-4 is what kind of liquid? It's a superfluid, which means what? It flows without viscosity. And what is viscosity?
Friction.
It's kind of like internal friction. Well, if you cool it low enough and all the particles drop into the ground state, can they lose any more energy?
No.
No, because they're in the ground state. They can't lose any energy. So what's going to happen if it starts to flow? It just continues to flow. There will be no friction in the system, no viscosity. Okay, pretty cool. Okay, which means it actually starts crawl up the containers and out of the container. It's really bizarre. Okay. Now what we're going to do, we're going to work out each of these cases here. And we're going to get our system is going to become one energy level. So I might have a system with a whole bunch of energy levels, and I'm going to say, oh, my system is one little energy level. Now I want the average number of particles in that tiny one little energy level. When we do that for here, we get the Bose-Einstein distribution, and then we can help etch them. Okay.
Yeah.
And then we do this over here, we're going to get the Fermi-Dirac distribution. That'll help out Matt and Elmo. You're an Elmo too, right? Okay. Okay. That'll help out the Elmo people. Okay. And then after that, we're going to say that we've been good little citizens of statistical mechanics and go on to energy landscape. Okay, have a good day. Yeah.